Hi, the last video of this topic, I examined correlation. In this one, we'll move into the exciting world of regression. Regression is one of the oldest predictive modeling or supervised learning techniques. Yet it remains a really useful tool for predicting a numerical outcome and is widely used. In fact, many modern machine learning approaches are some generalization or some offshoot of linear regression. So it's sort of like, cornerstone, a more basic technique on which many other techniques are standing. Take a look at these three plots. We have three graphs out here that indicate a scatter plot of points. Each one of these scatter plots has on the y-axis sales, and on the x-axis, some variable that is used by marketers. Specifically, we have three advertising variables. In the very first graph, if you look carefully, you'll notice we have a blue line indicating a line that is going through the red dots or the scatter plot. This blue line represents the direction in which the dots are going. Based on this blue line, one can tell as one advertises more on TV, sales go up. In other words, there is a positive relationship between TV advertising and sales. Furthermore, one can see for radio, there is a similar relationship at play. This line isn't as sloping as much as the previous line for TV, but there is some level of a gradient here. So this relationship is strong, but if you consider this relationship strong, maybe you should call the previous one, stronger. So I'll put 2 plus signs for TV. Let's move on to the right, and now you can see a third scatter plot, one for newspaper advertising. As was observed for the previous two plots, as newspaper advertising goes up, sales go up too. However, at a slower pace. Therefore, let's identify this as a positive relationship. Let's just use 1 plus out here to represent a correlation, a relationship that's positive, but not as positive as the first and second relationship. So here we have the slope representing the strength of relationship between the two variables we're looking at. Now, correlation is very flexible in that it argues for a bidirectional relationship. In practice, we're really interested in examining unidirectional relationships, more specifically, cause and effect relationships. Thus, one is frequently interested in looking at whether X causes Y or not, the extent to which TV advertising is driving sales, or radio advertising is driving sales, and so on. As it turns out, there is no sure way to know this relationship is indeed causal, at least not based on statistics. In fact, no statistical technique or method or analysis technique will be able to confirm that what you have is a causal relationship. The only way to know there is for sure a cause and effect relationship is to conduct a research experiment, a randomized controlled trial, or an experimental design. Or there might be some good theory that might support the cause and effect relationship's existence. That being said, it is convenient, and that's part of the reason we treat regression as though there is a cause and effect relationship. But just kind of bear in mind the caveat that you really can't be sure based purely on the research, based purely on the analysis technique. In other words, just because you run a regression doesn't mean you're looking at a cause and effect relationship. So the regression before can answer questions like, is there a relationship between advertising budget and sales? Indeed, there is. How strong is the relationship? It's a strong one, and stronger for TV advertising than for radio, which in turn is stronger than for newspaper advertising. How accurately can we predict future sales? Well, look at the points. Are they pretty close to the line? They're pretty far off from the point. If they're very far off from the point, it indicates your accuracy isn't going to be as strong. All the relationships look linear based on the trend of the data. Is there synergy among the advertising media? In other words, do the variables interact in influencing advertising or not? That we can't tell solely based on the graphs. Let's dig deeper into this topic by understanding the mechanics of estimation and linear regression. Rather than getting too deep in the weeds about the math behind regression, we'll try and understand regression in a visual manner. Before that, a little bit of math. The goal of regression is to estimate parameters of the population regression equation. An equation that looks as follows: y equal to beta 0 plus beta 1x plus epsilon. Here x is a predictor and y is the outcome. Also known as x as being the independent variable and y the dependent variable. Beta 0 and beta 1 are the parameters that will be estimated, also known as regression coefficients. Eta is a random error. We typically use a technique called ordinary least squares to figure out what are the optimal values for beta 0 and beta 1. Let's examine this OLS estimation process visually. To give context to the problem, let's examine a data set of deal proneness gathered by me and my co-authors. We were interested in examining the effect of deal proneness. Specifically, we were curious to see if children were in any way like their parents with regard to deal proneness. You've all known and observed that tall parents have tall kids, and parents impart upon kids various habits, behaviors, and so on, so forth. We were curious to see if children in some way inherit marketplace behaviors, specifically deal-prone behaviors. Put differently, if the mom is predisposed to buying on deal using coupons, then is the child going to exhibit similar marketplace behaviors or deal-prone behaviors? So we're interested in seeing if the mom is a coupon queen, is the daughter also a coupon princess. Okay, so what we did was we handed out some questionnaires to a couple of college students. They answered some 32 questions on deal proneness. Then we had them take the questionnaire to their parents, who filled out an identical questionnaire, polling them about 32 items on deal proneness. We averaged the scores and we got the numbers that you're seeing on your screen, and more, of course. There was more data than that. Okay, so the first thing we did was to plot the data, as you should whenever you get you want to examine the relation between two variables. The first thing you do is you create a scatter plot. On the x-axis, we have the parent's deal proneness, and the y-axis, the child's deal proneness. Our goal here was to understand, this is good, so is there a relationship out here? So before understanding if parent's deal proneness is influencing child's deal proneness or not, we thought, let's identify a baseline. What's a baseline? So in other words, if we had no information about the parent's deal proneness, we had to make a prediction about the child's deal proneness. Our best bet would be to imagine any given child's deal proneness is typical, that is average. So average is, generally speaking, a safe choice, safe unbiased choice for predicting in the absence of any other information. If we had no other information about, let's say parent's deal proneness, one could assume any given child's deal proneness is the average. This horizontal line then represents that average, or what you call a baseline model. Well, what we really have is, of course, we have parent-steal pronouns. Let's leverage that data. We can do so by constructing a regression model, which looks like this blue line. So this blue line represents, in a sense, the best of many possible lines that can go through these points. In fact, it's called a blue line. Where blue is an acronym for best linear unbiased estimator. This blue line that you're seeing is really good and really optimal because it has a number of characteristics that make it really good. Specifically, this line is such that it gets as close to all points as is possible, as is mathematically possible. More specifically, in the following plot you see, if you were to draw lines from every dot to the regression line, you would add up those distances. So think about, again, all the distances that you've got from the regression line to the dots. You add up all those distances. You'll see some of them are below the regression line, some of them are above the regression line, and so on. Therefore, the ones below would be negative in valence, and the ones above would be positive in direction. If you add them all up, your sum, the sum of all these error terms would be 0. Now, that's good. Okay, so that's one property of this regression line. Another one is that if you were to square every one of these errors you see, so say E1, E2, this distance is also known as E, or error. If you were to square every one of those elements, E1, E2, E3, and then add them all up, so E1 squared plus E2 squared plus E3 squared, you represent that in short form as sum of all these squares, so sigma EI squared, the sum of all the EI squares. Now, this expression you're going to get for regression for the blue line is minimum. So if all lines can go through, the sum of squared errors for regression line is minimal, and to that extent, this line is optimal. It's the best of many different lines you can construct. Okay, well, in order to assess how good this regression line is, one needs a baseline for comparison. So we're going to go back to our baseline model. Imagine you were going to use that baseline model. Imagine you had no other information about parent-steal proneness. You would then use the baseline model, and you would evaluate a similar set of squared errors, which would look like this. Here we're drawing drop lines from the baseline model to every single dot in the graph. And then you would square every one of these distances and add them up. This would give you sum of squared total errors, okay, or total sum of squared errors. So what we have is right now two measures. The measure for the green line, let me abbreviate that as SST. SST then represents, in a sense, all the error in prediction using that baseline model. And the blue line is representing SSE, that is, where SSE is the total error of all the predictions, or some metric for error of the regression line. So our goal here is not to describe, not to compare the regression line to a model that predicts every point perfectly, rather to compare the regression line to a baseline model. So we can do this by saying, let's do SST. So how bad is a baseline model minus SSE, and divide that by SST. This fraction you can simplify to 1 minus of SSE divided by SST. This expression you're seeing now on screen is also commonly known as your R-squared measure. So R-squared represents how good the regression is, and ranges from 0 to 1, where R-squared means the model is perfect, and 0 means is no better than the baseline model. In other words, if the blue line and green line coincide, your R-squared would be 0. Ideally, we'd like to have R-squared be as large as possible. Okay, so with that behind us, let's go into examining a bit more about regression. Specifically, we'll examine the twin goals of regression: prediction and inference. There are situations where you care a lot about prediction, and situations where you care a lot about inference. Predictions is just that. It's about predicting the outcome variable using a bunch of predictors. Under prediction, here's what we do. We answer the question, is there a relationship between the outcome and predictors? We conduct a statistical test to see if at least one of the coefficients is non-zero in the case of multiple regression. And so our hypotheses look as follows. We examine whether the predictors influence the outcome variable or not. And this is examined or assessed by looking at an F to F statistic and a corresponding p-value. The p-value is less than 0.05. We would conclude that the predictors jointly have an influence on the outcome variable. Moving along then, once we've established that all the predictors together have an effect on the outcome, one would ask the question of how strong is a relationship? Strength is assessed using R-squared, where the larger the value of R-squared, the stronger the relationship. R-squared ranges from 0 to 1, which is why it is tempting to often interpret R-squared as a percentage value as well. This is also done. So folks might call a 0.5 R-squared as 40%. And that's a fair kind of characterization. The heuristics we typically use for R-squared are as follows. If the model R-squared is less than 0.1, that is seen as being weak. If it's 0.1 to 0.5, seen as moderate, and a strong model will be one with R-squared more than 0.5. Now, note here, we're referring to R-squared. R-squared for regression is not the same thing as R for correlation coefficient. In one particular instance called simple regression, the correlation coefficient squared is in fact the regression R-squared. But aside from that exception, these are not directly linked, nor are the heuristics. So pay close attention to these heuristics being for R-squared and not for R. They're different. One can go on then, once one has examined how strong the relationship is, examine how accurate the predictions are using some other metrics, like metrics that actually look at the error component. You can summarize the error as sum of squared errors, mean squared error, or a more commonly used metric called root mean squared error. These metrics, however, are not useful for comparisons across samples. Let's look at what inference is. Inference is about meaning. What is the regression conveying? What is it implying? What is it, again, in layman's terms, what does it imply? What does it mean? Well, one question commonly that might arise is good to know that the predictors jointly influence the outcome, but obviously one may also want to know if there are 10 predictors, 10 independent variables, which one of the independent variables has an influence on the outcome. One can then examine individual variables and their coefficients to determine which of the variables has an effect on the outcome. This can be ascertained by looking at the p-values for any given t-statistic. Furthermore, one might want to understand how to interpret a coefficient. If your equation looks like y equal to b0 plus b1 x1, what does b1 mean? Well, what b1 means is the following. If x1 changes by 1 unit, y will change by b1 units, holding all other variables constant. That's the interpretation of the regression coefficient, or b1 in this case. Another goal of inference is to understand the relative strength of variables. If there are 4 independent variables or predictors that are driving an outcome, well, which of them is the strongest predictor? One can do this or determine this by looking at the standardized regression coefficients for the model. Now, bear in mind, there are a number of assumptions of regression. Generally speaking, regression is robust against small violations of assumptions, but ideally speaking, you should probably check these out before going forward. And we're not going to spend too much time on this because it's far beyond the scope of this class. So moving along, we're next going to look at simple regression in the next video. See you there.